So let's get started. Um, we are today on September 10th. We're going to start the second module, Solutions of Linear Algebraic Equations. I originally planned to do 3 lectures on this topic. I have reduced it to 2 because there are only 3 methods that we are going to cover. And the quiz is 1 week from today. So next Tuesday is your quiz on this topic. So 3 methods, 2 questions. So you'll be tested on 2 out of 3. And after the quiz, we'll do some MATLAB programming related to this module to wrap it up. Last lecture, we had the quiz. I also assigned self-study on 2 methods, which I asked you to study. And hopefully on Thursday, I'll try to find 10 minutes to squeeze in these 2 methods to quickly run through them, and you'll be able to study them at home. Or you might have already studied and we just will review it, okay? I did this because I wanted to give myself 4 full lectures for statistics, which is a pretty important and elaborate topic. And we'll have the first exam coming up on October 8th, third quiz on October 3rd. And I also might remind you that homework 1, which is one programming exercise indicated at the end of the document that is due next week. That is next Tuesday when you come for the quiz, you should have your homework 1 ready to submit. Okay. Any questions about lot going on here? Homework, quiz, and an exam coming up on October 8th. Okay. Are you all downloading this syllabus after every lecture? Because I update it every time. Every time I have a new link, I paste it and repost the file. Okay, so don't be stuck with an old file. All right, so I'll stop the screen share here and go back to the whiteboard. Today, mostly we are not going to have any computer involvement. My plan is to cover these 2 methods, Kramer's rule and Gauss elimination today, and then Gauss seidel iteration next lecture, so that you'll be ready for your test on Tuesday. Okay. So 3 methods, 2 questions. That's our formula. All right. So if you have an equation, like a set of linear equations that look like A11 x plus A12 y and A13 z equal to B1, A21 x plus A22 y plus A23 z equal to B2, A31 x plus A32 y plus A33 z equal to B3. So these are linear algebraic equations which you encounter in your engineering problems. Can you give me some examples where you are required to solve a system of linear equations in order to get your solution? Instances or examples. Where do you encounter equations that look like these? Sorry? Matrices. Okay, matrices are a way of representing them. That is, you can equivalently write this as A times X equal to B, where A equals A11, 12, 13, 21, 22, 23, 31, 33. And this matrix X is a column vector. X, we'll say X, Y, Z. And B is another column vector, B1, B2, B3. What I'm saying is AX equal to B is a shorthand notation for writing it out like this. I'm sure you saw this in your math class before. This saying that it is matrices isn't really an application, it's just a way of representing it. Where have you encountered this in your other engineering courses, or have you encountered this in your engineering courses? Think back to the courses you have taken so far, or your internships, or your jobs, wherever you have encountered this. Yeah. Trusses, very nice. I was hoping you would say that. So if you have different components that share links, if you do a force balance on this, you will end up with components that are contributed by each element, and you will end up with a system of equations, each for one of the joints. So as many number of joints, you will have as many number of equations. So that is one very good example. Trusses or statics, basically free body diagrams, which are connected to each other. Which are, can you think of any other application? Yeah.
I think there was something in circuits that we did.
Brilliant. Can you elaborate?
No.
No? you had me at circuits. So that is also correct. So if you have a circuit that has multiple loops, and so on. If you write a current balance for each loop, that is, if you write Kirchhoff's current balance for each loop, you can write an equation that connects these circuit elements through a current. So suppose this is I1, this is I2, and this is, let's say, I1 again. So you'll have I3, and you will have a current balance that is for I1 that involves these elements and I2 that involves this element. And you can write as many equations as there are loops. So they'll all end up looking like this. So what we are seeing here is not really the physics of how you end up with a circuit or with a truss, but if you end up with those equations, how can I give you some recipes to solve? If you punch it into your calculator is going to give you some numbers, but as an engineer, you should be able to cross-check those numbers and know the real math that is programmed into your calculator, which is what we are going to learn. Okay, so let's start with the easiest of these methods. Okay, so if you have an equation that looks like this, Ax equal to b when written in matrix form, the first thing you got to check is whether this system has a solution at all. There are some systems which don't have a solution. Like for example, if the determinant of A is 0, then the system has an infinite number of solutions. What do we mean by that? If you take this matrix here, when the determinant of this is 0, what does that mean? Take a pause, listen. If this matrix has a determinant 0, it means any two rows are probably either identical or just multiples of each other. If, for example, you have A21 is nothing but 3 times A11 and A22 is 3 times A12 and A23 is nothing but 3 times A13. If that is the case, if two rows are identical, this matrix has a determinant of 0. But in terms of the physics or in terms of your equations that represent the actual physical situation, what does it mean to have two equations which are really the same? You have three variables. You have three equations, but turns out two are duplicates of each other. What does that mean?
Same direction.
What that means essentially is although you have three equations, you don't have enough information about three variables. That's what literally it means. You have three equations. Each equation is a piece of information about each variable. If you have n equations or if you have n variables or three variables, you need to have three linearly independent equations. But if you don't, it means any one variable can be a free choice. So you can choose x equals 4 and then compute y and z. You can choose x equals 5 and then compute y and z. Each choice of x leads to a new solution, which is what we mean by an infinite number of solutions. Okay. So first step is check if the determinant is zero or non-zero. If determinant of A is non-zero, okay, Kramer's rule, obviously Kramer is the guy. Kramer's rule provides a simple means to calculate the solution x. That is the first variable x is, take this matrix, replace the first column with B1, B2, B3. Is B1, B2, B3, and keep the rest of it the same. A12, A13, A22, A23, A31, 33. Sorry, 32, 33. X is this replaced or modified determinant divided by the determinant of A. Or divided by, I'll write it out. Just I'll move out of your way shortly, sorry. So this is x obtained by replacing the first column with the right hand side. I'll give you a moment to write this. As you are writing, did you catch my numbering convention? When I write A, I, J, what I mean is I is the row number and J is the column number. So the position 1, 1, this is position 1, 2, 1, 3, 2, 1, 2, 2, and so on. The reason I'm saying this is later when we generalize this for a matrix n by n, it'll be obvious. So we'll start with 3 by 3. So x is given by a modified determinant with the first column replaced. So I'm going to write it out in words. X is given as the quotient of a modified determinant A and determinant A itself. When we say modified determinant A, what does that mean? It means column 1 is replaced with B1, B2, B3. If I were you sitting down and taking notes and learning this for the first time, this is exactly what I wish I know. So that you can read this and calculate x. We didn't really go into the theoretical underpinnings, how Kramer got this. We didn't do any of that. I'm just giving you a recipe. Here's how you solve this. Okay. So just keeping it clear what we are doing here. We are not trying to learn the math underlying this method. So if this is x, by extension you can easily write y and z, can't you? Now for y, which is the second variable in your solution matrix. So this is the solution matrix or solution vector. This A is the coefficient matrix. I really don't believe in giving a name for B. It's just the right side. So Y would be A11, A21, A31, B1, B2, B3, A13, 23, 33. Similarly, you can write C equal to column 1 unchanged, column 2 unchanged, and then column 3 divided by determinant of this. You take a picture of this. This is your cheat sheet for Kramer's rule. All the information we'll need is here. Okay, we'll do an example. Any questions so far? Like so far, I've not really taught any concept, just giving you a two-step process. Check if the coefficient determinant is non-zero. If that's the case, get xyz. Okay. Are we all familiar with calculating determinants for a 3 by 3 matrix? If not, we'll learn now. Okay. All right. This is an example from the book. 0.3 x plus 0.52 y plus z equals minus 0.01, 0.5x plus y plus 1.9z equal to 0.67. 0.1x plus 0.3y plus 0.5z equal to minus 0.44. In matrix form, this would be Ax equal to B, where A equals, so remember this is position 1, 1, this is position 3, 3, 1, 3, 1, 2, 2, 1. I mean, rest you can fill out, right? So this is 0.3. It's a really simple method. All you have to do is be methodical about it. This is the matrix. So step 1, Write it in matrix form if it's not already given to you that way. Step 2, check, or not even check, let's say compute determinant of A. Compute determinant of A. Those who know, that's fine, that's good. For those who don't know, here's a refresher. You have your indices, right? 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, 2 and 3, 3 and 1, 3 and 2, 3 and 3. Those who know, just go ahead, compute the determinant. For those who are, you need a refresher, this is determinant of A is equal to A11 times minus 1 power 1 plus 1 multiplied by, so if you are taking A11, strike out that row, strike out that column, the remaining matrix or determinant of A22, A23, A32, A33. And then plus the next element I'm going to consider is A12 plus A12 times minus 1 power 1 plus 2. So if you have considered A12, you need to strike out the first row and now the second column and the remaining elements A21, A31, A23, A33. Look at these two steps and tell me if you are with me so far. Maybe you already know this, which is okay. Plus, can you write the next term and then look up? If I say this is determinant of A, would you agree with me? Right? Like, does this look consistent to you? Okay, so now we are going to do this with numbers instead of symbols. Determinant of A is, what is the first term? 0.3. So if you see here minus 1 raised to the power 1 plus 1, that makes this 1. Whereas the second term is minus 1 to the power 3, which makes it a negative 1. And the third term is minus 1 raised to the power 1 plus 3, which makes this plus 1. So it will be alternating plus and minus. So 0.3 multiplied by 1 times 0.5 minus 0.3 times 1.9. Okay, minus, what's the second term? 0.52 multiplied by 0.5 times 0.5 minus 0.1 times 1.9. That's the second term. And then third term is plus 1 times 0.5 multiplied by 0.3 minus 0.1 times 1. What is this? This is, you can easily do this in the calculator, of course. 0.5 minus 38, 47, 57, 0.57 minus 0.52 times 0.25 minus 0.19 plus 0.15 minus 0.1. Can you tell me what the value is? Are you getting minus 0.0022? Yeah. So good. So you have the determinant of A, which clearly isn't 0. Okay. So then you would say X equal to, I made a mess of this. I'm going to clean it up. Equal to 0.3, 0.52, 1, 0.5, 1, 1.9, 0.1, 0.3, 0.5. Okay, what is X? Tell me words. What will you do now? You take the determinant of A or the matrix A, replace the first column with the right hand side values. A very simple procedure. So I would write X is the determinant of minus 0.01, 0.67, and then minus 0.44, and the rest of the elements being same as what A is, which is 0.52, 1, 1.9, 0.3, 0.5. This divided by determinant of A. Can you compute this and just tell me the answer? I'm not going to work out the steps. I want you to go from here to saying what the numerator is divided by the determinant of A, which is minus 0.0022, and then what the final answer is. Can you please try? The real simple method, if you can do the calculations without making mistakes. Remember this column coming exactly from the right hand side. Okay. Yeah. Anyone? What are we getting for the determinant of this numerator?
I have 0.0327.
0.0327. Yep. 0.0327. And if you do the division, what are you getting for the value of x?
Negative.
Negative 14.9. Right? So that wasn't too complicated, right? It's a matter of computation, punching in the numbers and getting the numerator and then getting the actual value. So please repeat that for y and z as well. Are you all able to calculate determinants or at least making progress towards it? Do you have an answer? Yeah, say it. Oh, you weren't sure you were supposed to speak. You're allowed to speak. Tell me.
Oh, I just have the overall answer. So y I got was negative 29.5.
What did you get for the numerator? You should have got that as an intermediate calculation.
Point 0.649.
Okay, and for Z,
Negative 0.0435.
so others who are trying, there is no real not very complicated thing. It's about evaluating four determinants exactly. Determinant of A, and then for each of x, y, and z, or x1, x2, x3, whatever it is called, for each variable, you need to evaluate another determinant and then get the value directly. Okay, very simple method. The key pitfall is if you have to first compute the determinant of A and make sure it isn't zero. If it's zero, this method will not work. That's obvious, right? So if I have to summarize to wrap up this section, write down the system of equations in matrix form, get the coefficient matrix A, coefficient matrix. Step 1, get the coefficient matrix. Step 2, compute the determinant of A, ensure that it is not zero. If it is not zero, that implies there is a unique solution for x, y, and z. What do I mean by unique solution? I mean there is exactly one combination of x, y, and z which will satisfy this equation. You can either have a unique combination or no solution or an infinite number of solutions. If this determinant is non-zero, there is a unique solution for x, y, and z exists. And then third step is just computing x, y, and z by replacing the first, second, and third columns. So this is the wait. This is first column. Replace first column with the right hand side. I think I wrote it wrong. 0.67 minus 0.44. Here you would replace second column with the right hand side values, and here you would replace the third column with right hand side values. So there's again one more example or like a cheat sheet for what you need to do for this course. Actually, this module, this entire module is just a cheat sheet. There is no real concept. It's just like recipe after recipe. Okay. So please make a note of this. I strongly urge you to go home, try more examples on this method as well as the other methods. You can take the same problem and solve it using 3 methods to cross check your answer. Is everybody still working? Should I wait? Can I move on? You need a minute more? You're okay? Others, can we move on? So let's take the same problem and learn another method using this example. Okay, so same problem. We are now going to learn the second method in our list, which is called, among the various things that Gauss did, it's called Gauss elimination method. So drop your pencils, please listen. It's a very simple method, but it just involves a lot of steps. And I want to do the steps in front of you so that you can understand and you could do it on your own. So please take a break, don't write. Okay. So look at these 3 equations, 1, 2, and 3. Let me ask you a series of questions. When you get a system of equations, arrange them such that the first term is non-zero. Just you can arrange them. You can write the third equation as first or the second equation as first. It is no restriction. What you need to do is make sure that this term, the first term in the first equation, isn't zero. Just rearrange it that way. And then if I ask you the question, look at this term and look at this term. Look at this coefficient, look at this coefficient. What manipulation should I do? Like, for example, multiply the first equation by a constant, multiply the second equation by a constant, and then if I subtract to eliminate the first term altogether. How do I make the coefficients of x the same in both the equations? What do I need to do here? I have 3 or 0.3. If I multiply by 0.5 here and do it the other way, multiply this by 0.3, they'll end up both with 0.15, and then you can subtract, right? So I'm going to write multiply equation 1 by 0.5 and equation 2 by 0.3, which will give me what? 0.15x plus, what is 0.5 times 0.52? I need to keep my calculator handy. 0.5 times 0.52. Okay, 0.5 that's 0.26. 0.26y plus 0.5z equals minus 0.005. And then this second equation becomes, so I'll write this is 1 modified and then 2 modified, 0.15x plus 0.3y plus, what is 1.9 times 0.3? 0.57 z equals 0.67 times 3 or 0.3. 0.201. 0.201. Okay. And the third equation still remains the same. I'll just rewrite it here. 0.1x plus 0.3y plus 0.5z equals minus 0.44. So you have gone from the original set to this set, which is still equivalent because all you did was to multiply by constants. So if you look at this modified set of equations, what immediately jumps to you? If you look at the modified, yeah,
In the third term. The third equation, we can return to the first.
um,
And
that okay, actually that is a coincidence. What I was hoping to find, or what you will always find, is that these two terms are now equal, right? You can subtract them and you will end up with an equation which doesn't have any x, right? So if you do equation 1 minus equation 2, you are left with 0.26 minus 0.3, which is minus 0.04 y plus, this is 50, this is 57, minus 0.07 z, and this is 201, this is 5, so this is equal to minus 0.206. Right? You eliminated what we just did, eliminated x from equation 1 and 2. So you have a new equation which involves only y and z. Okay. Right. Now take a break. Just listen for 1 second. You did this between equation 1 and 2. There's nothing that's stopping you from doing the same between 1 and 3. Right? You could have done the same between 1 and 3 to eliminate this coefficient and end up with one more equation that has only y and z. Okay? This process of sequentially eliminating one variable at a time, that is why this method is given the name elimination method. Okay? And you don't have to do this like very tediously by writing it out. I'll multiply this by that and so on. We can do this with matrix operations in a neat and efficient manner without having to write so many words, which is what we are going to learn now. Okay, so this is sort of explaining how the method itself works and then a cleaner way to implement it or cleaner way to do it. So start here. Write out an augmented matrix. Augmented matrix, which looks like this. The coefficients 0.3, 0.52, 1, and then take the right side and make that the fourth column, minus 0.01, and then 0.5, 1, 1.9, 0.67, 0.1, 0.3, 0.5, minus 0.44. Step 1, write out an augmented matrix. Always start here. Okay. Now, okay, we'll call this row 1, row 2, row 3. Row 1, 2, 3. Okay. What is our goal? Our goal is to reduce the matrix to a form where you have A11, A12, A13, B1, 0. I'll write A22 star, A23 star, B2 star, 0, 0, A33 star, B3 star. Our goal is to reduce the augmented matrix to a form that looks like here. Why? Why should we do that? What is the use of reducing it to a form that looks like three zeros? Essentially, A21, A31, A32 are made to be zero and reduced to this form. If I do this, so what? Think and tell me.
You're able to solve all three equations, because you, with there's only a z term in row 3 now.
Right.
But you'll be able to find that in B, you plug it into row 2, you'll be able to find y, then do the same thing with row.
So you would, so what he is saying exactly is right. This is equivalent to writing A11 x plus A12 y plus A13 z equals B1, A22 star y plus A23 star z equals B2 star, and A33 star z equals B3 star. This is, you have reduced your original set to this form. Like you said, the third equation involves only z, so you might as well just write z is B3 star divided by A33 star. Right? And then you would use this z value back here and try to write y equals B2 star minus A23 star times B3 star divided by A33 star. You can and then divide the whole thing by A22 star. That is, you got z first. From z you are getting y. From y and z you are going to take and get x. So from here we can also get x. I'll let you write up to here and then make a point which will kind of give us a recipe what to do. If you are done writing, I need to know so that I can continue, talking. Good. Okay. Good. Good. Okay. Have you finished writing? Yeah. Okay. All right. So this process where you take a matrix that starts out in this form as a regular set of equations, you reduce it to this form. This process is called elimination. That is, you are eliminating the coefficients one at a time. So we call it elimination step. Okay. This form here, where you have, if you just consider these 9 elements, this is your diagonal, and the lower part of the anything that is below the diagonal is 0. So we call this lower diagonal form. And once you reduce the augmented matrix to the lower diagonal form, you can do this operation, which is called back substitution. It's a very obvious name. You get one, you substitute it back, you get one more, substitute them back, get the third. So it's called back substitution. Okay, So what you need to practice is how do you go from here to this lower diagonal form? That if you figure out, rest is just child's play. Okay. If you write down these three pieces of information, we can start here and work our way to getting here. Are you ready? Okay. So can I erase this side? People are still writing. Can I erase this side? Good. Okay. All right. Look at that augmented matrix and tell me how do I. You're going to keep row one intact. That is obvious, right? Row one is not going to change. How do I make this element 0? I need to subtract R2. I need to subtract R2 minus some constant times R1 to make this 0. What constant should I multiply? Okay.
Can't you multiply both of them?
We are going to keep R1 intact. We are not going to
Not change it all.
change it at all. Okay. So if I write, this is A22, this is A11, A12, A13, B1, A22, A23, B2. This is the original matrix.
Is your first A supposed to be A2?
Correct. Thank you. Good catch. Okay, this is the original matrix. I want to get rid of this A21. What I will do is I'll take R1, divide it by A11, and then load it with A21. So if I do R2 minus, if I do row 2 minus row 1 divided by A11 multiplied by A21. Similarly, I can also do, while I'm at it, I can also do R3 minus R1, remove A11 and load it with A31. So this is in terms of symbols. Let's do it in terms of numbers. My row 1 is going to stay the same, 0.3, 0.52, 1, minus 0.01. I'm going to take 0.5. Look at this, 0.5 minus 0.3 divided by 0.3 times 0.5. What is this? 0. That's the intention, right? By design, it is 0. By design, the first term is made to be 0. But what about the second term? Okay, this is A21 star. What about A22 star? A22 star will be 1 minus 0.52. I have to divide by A11 and load it with A21. What is this? This won't be 0 exactly. Okay, this in fact almost never will be 0. 1 minus, can you tell me this? Zero, 0.48. Sure. Who said that? Yeah, 0.48. Okay,
Or no, it's not, it's pointing.
0.8.
Yes.
Okay. 0.8. Anyone else is getting that? Okay, we'll take it for now. A 31 star. You compute it and then look up. I won't say just don't look up, first do the calculation. What are you getting for this place? A31, A31 star. You're getting 1.5. Others? I mean, you understand this, how this came about, right? Nobody is unclear about this step. Punch in the number and tell me the answer. 2, 2133.
I got 2, 3.
233, sorry, yeah, 233. Yeah, 0.233. And what about B2 or B2 star? Same logic. B2 star is
For the, A22 star, I got 0.13.
0.133. Okay, not 0.8. Okay, 0.133. For B2 star, what are we getting? B2 star would be 0.67 minus 0.01 times 0.5 over 0.3. Can you compute this?
687.
0.6870.
Yes, 0.68666666.
Okay, let's round it at 4 points. 6867. 0.6867. One more method where you have just tested whether you can punch numbers correctly and quickly. Like not deep concepts here, just number crunching. Are you feeling tired? It's natural. I feel tired. Like it's just like so. You can't miss one number. You miss one step in between, you get one number wrong, everything else following it is going to be wrong. So you have to be careful. Okay. All right. So you did row 2. Okay. Now you have to do row 3, but right away both numbers will not become 0. the first thing you can aim for is try to get A31, try to make A31 0, and then see whatever A32 and T3 come out as. Okay, how do you do that? If you want to make this element 0, I would take 0.1, I would write 0.1, I'm sorry, I'm going to write A31 star is 0.1 minus, I'll take 0.3 divided by 0.3 and then multiply it by 0.1. This will make it by definition exactly 0. So we want this to be 0. But that will not automatically guarantee the next term is going to be 0. What is the next term? A32 star is 0.3 minus 0.52 divided by 0.3 times 0.1. What happens to this 0.3? To do this calculation, I have A32 star to be equal to what? Louder please. 0.1267. You can say it loudly. There is no score or credit for class participation. So it's not like because you say or don't say, I'm going to punish you or reward. Just say what you feel or what you get. 0.1267. And then A33 star is going to be 0.5 minus 1 times, I have to divide by 0.3 and multiply by 0.5, no, multiplied by 0.1, which would be 0.5 minus 0.3333, which is like writing 0.17 or 7661. 0.1667. That is A33 star. B3 star is, what is B3? Minus 0.44 minus of 0.1 multiplied by 0.1 over 0.3. Is correct? Minus 4367. All right, so here is your original augmented matrix before you started doing your the process, the elimination process. It's here. After one round of eliminations where you have made these two elements to be 0, you have this. Okay. Of course, our goal is to go one more step where we want to take this element A32 and reduce that to 0 before we start the back substitution. Is this intuitively making sense to you so far, the sequencing? Okay. So now you can leave R1 alone, as we always do. You can even leave R2 alone. You just have to modify R3 once. Okay, so I'll write R2 dashed. Now this is R3 dashed. Okay. Can I erase these parts? Can I erase these? Now, don't pay attention to the first element. Pay attention only to the second element. That is, you want to write R3, okay, R3 dashed minus whatever the value of 0.1267, sorry, whatever the value of this is, A32 star, A32 star. So you need to take R1 and you need to divide by A12 and multiply it by A32 star. What would that be? If I take point, if I want to compute, I'll say A32 star star, that is two modifications. That would be 0.1267 minus 0.52 divided by 0.52 multiplied by 0.1267, which is 0 by definition. That's the intention, right? So if I write the next round, 0.3, 0.52, 1 minus 0.01, 0, 0.1333, 0.2333, 0.6867, 0, and then this is also 0. A32 star star. What do you do about this? You have to compute A33 star star, that is in the second round of modified values, that would be 0.1667 minus 1 multiplied by 0.1267 divided by 0.52, which is equal to, you tell me. You have a number? Yeah, tell me.
-0.77.
Negative point
0.77.
0.077. One more decimal point.
0.769, yeah.
0.769. Yeah. Okay. So this is negative 0.0769, which is A33 star star. And then we want B3 star star. That is B3 after two modifications, which is B3 star star is you have to take this minus 0.43 0.1267 minus of 0.01 times 0.1267 divided by 0.52. This is A33 star. This is B3 star. This is B2 star. This is A22 star. This is A21 star. Each star represents a next iteration. What is this number?
Negative 0.4343.
Negative 0.4343. So this is negative 0.4343. Great. We now have the augmented matrix manipulated twice to end up with a lower diagonal form in which everything below the diagonal is 0. This is like 90% of the work to get here correctly. Okay. What do you do next? Start the so-called back substitution. Get Z, use it to get Y, use them to get X. Go in reverse. Okay. So let's complete it. I'm going to write what I said. After 2 rounds of manipulation, we have the augmented matrix reduced to the lower diagonal form. That is, remember, lower diagonal form means displaying some knots in the process here. This is the lower diagonal form, which is what you got here. Now, next is back substitution, which is get Z, use it to get Y, use it to get X. So minus 0.0769 times Z equals negative 0.4343, which implies Z equals what?
5.6476.
5.6476. Did you say 5 point?
Yeah.
That doesn't, that's not consistent with the value we got with the other method. (43/7) is still like 6 point something. But how did we end up with? Okay, we have a problem. We have a problem not with the method, but in some of the intermediate calculation. We know that we did the same problem using the Kramer's rule, right? So your answer has to be the same using both approaches. So we did something here that is not giving us a consistent value. Are you seeing the problem? Right? So what I would do is I'll work it out myself, get you the steps written down in a sheet of paper, scan it and post it on Canvas. I want you to try by yourself and then look at it. It's not rocket science. We missed something in it. Okay, it's just a few numbers where we could have made a mistake, but the procedure still remains the same. I'm not able to actually illustrate it to you by doing Z and Y and X, which is frustrating, but we can get to it in the next lecture. So please try this again. I'll also try and I'll post the solution. Did you find something? Okay.
And I got an answer, so it was like 2/10 off from the correct.
Okay, but what are we missing here?
Well, I multiplied R2 by the A31, or I multiplied R2 by negative 0.1267. And then I added R3 times positive 0.133. And then I got that second spot in A33 or A32 star. Wait,
Wait, one second. Are we both agreeing up to here?
yeah.
Okay, what are you getting for this one?
That one I got negative 0.00741.
0074. And then this value?
Negative 1453.
1453. If we use these values, I would still like to use them to make my point. Okay, if you don't mind. So I'm going to say this is negative 0.0074 times Z equal to 1453 minus 0.1453. This is R3 after two modifications. Okay, so what does that give us Z to be? Equals 19.6. Okay, so you have Z, go to the second row. Go to the second row, which is R2 after two modifications, which is 0.1333y plus 0.2333 times Z, which is 19.6 equal to 0.6867. So now if you rearrange and solve for y, what do you get? Negative 29.12. Okay. And then if you go to row 1, you're going to get 0.3 times x plus 0.52 times y, which is minus 29.12 plus z, which is minus 0.1 times 19.6, and that is equal to, this is 1 times 19.6, and that is equal to minus 0.01. If you do this, x equals negative 14.93. So this is the back substitution step altogether. The sequence is get z, then get y, finally get x. Okay, so thank you, Lauren. We were able to complete that example. So same problem we did using two approaches. Okay, these two methods, Kramer's rule and Gauss elimination method, are really simple to do by hand, but are really not that good for automation. So we will see this only as pencil and paper problems. Even if they appear in the exam, they'll only be a pencil and paper problems. On Thursday, we are going to see the Gauss-Seidel method, which is best suited for automation. We are going to see the method first, and then after the quiz, we'll do the programming. For the quiz, it's still pencil and paper, pencil paper calculator. Okay. Yeah. No, the Tuesday, next Tuesday. Next Tuesday, first 40 minutes is quiz. Remaining 45 minutes is programming, MATLAB programming. Okay. So Thursday, you're going to see the third method in our list. Okay. So please go home, do some example problems, practice. Okay. Without practice, you can't complete the quiz. All right. Thank you.